Good evening, my dear students. I am Dr. Enswati. Welcome to day 1 POC-II crash course. Thank you so much for joining in spite of your busy schedules. Before we begin, type POC in the chat to confirm your presence. And also please type where are you joining from. That is just type your city. So that I'll come to know from which place you are joining. Yes, thank you so much. So this crash course is mainly designed to help you to overcome your fear of organic chemistry, so that you will learn all the concepts step by step, okay, and so that you can perform well in your final examinations. So it is mainly examination oriented course. So this course is mainly meant for B.Pharmacy third semester students, those who are studying now pharmaceutical organic chemistry too. So it helps in two ways. You are a student who are having fear of organic chemistry and very much sure that you are going to fail in organic chemistry, because some students will be having that kind of phobia since beginning or since childhood. Okay, so if you are one such student, then this course is really meant for you students, because I strongly advise you that don't go deep into all concepts. Okay, every concept you learn as if you are going to attempt for a 2 marks question. Okay, so in that way, easily, what is the concept involved in that? If it is a definition, what is the definition? Example. Okay, and similarly, if any formula is there which has to be learned to get at least 2 marks for a particular topic, then learn that particular formula. So in that orientation, I'm going to give the course contents. So at least to learn 50% of the course, whatever I'm going to explain in these 15 days. So that is more than enough to clear this particular subject. Okay. The other category of students would be struggling between A and B grades. Okay, so if you are one such students, then this course will be useful to enhance your grades. For example, if you are a student who is getting repeatedly B grade, then if you follow this particular course, whatever the strategies that I'm going to explain, if you strictly follow them in your final examination, then there is more probability is there that you will be getting A grade. Similarly, the students who are already getting A grades, there is probability that they will jump to the next level. That is, they will get O grades. Okay, that is for sure, provided if you are going to follow all the strategies and the way of presenting the answer, whatever I'm going to explain in these 15 days. Because all the concepts, whatever I'm going to explain in these 15 days are examination oriented or examination important topics only. I'm not covering here the entire syllabus. Please make a note of it. Okay. Because the PCA syllabus, it consists of 5 units in POC-II subject, and each unit examination point of view, important core topics will be covered for 3 days. Okay, so like that 3 days, 1 unit means overall 5 units are there. So 3 5s are 15 days course. Okay, so that is how the course was designed. And as you are aware, the timing for this course is 6 to 6:45. That means 6 to 6:30 maximum I will take up the topic, and then last 15 minutes is meant for question and answers. Okay, so from time to time, as soon as one topic is completed or one topic is going on, whatever the questions or doubts that you are getting, you can, without any hesitation, you can post them in the chat. Okay, so from time to time, I will try to answer those questions. But if still, okay, if I'm in a flow and I could not see immediately the chat, okay, don't feel bad for that. But you keep on posting the questions, okay, and I'll be providing at the end of the each session, or even in the description, if you are watching this particular live as a replay also, then in the description I'll be providing a link for joining in WhatsApp group. Okay, if you feel that any of your questions are unanswered during the live session, then you can join in that WhatsApp group and you can also clarify in that particular WhatsApp group. Okay, and beyond this course also, if you need any assistance regarding pharmaceutical organic chemistry 2, or if you are having any backlog of POC-I, also I can help you for that. Okay, so without any hesitation, you can join in that particular WhatsApp group and get the answers or the support whatever is needed from me. Okay, so I hope this is clear for all. Okay, right. Whenever you are attending these live sessions, make certain things very sure. So the first important pointer is keep your notebooks and pens ready. Number 2 is keep water bottle along with you. Okay. And number 3 is inform your parents or family members well advanced that you are going to deep dive into this particular course for about 30 minutes or 45 minutes. Okay. Depending on your feasibility. And those people should not disturb you during the session. Okay. And the fourth important point is after attending every session, at least allocate 15 to 20 minutes before you attend for the next live session. Okay, for example, today after completion of this particular class, allocate at least 15 to 20 minutes, or just on the other hand, at least before you attend for tomorrow's session, allot at least 15 to 20 minutes for revising today's, that is day 1 content, that is previous day content. Okay, so that revision will be completed, so that there will be continuity whatever I'm going to explain, and you can easily understand in the next coming classes. Because most of the topics with respect to each unit, if you see, there will be continuity. One topic is connected to the other topic. So that's why revision is must. Okay, and this, so make sure of all these things so that you will get maximum benefit out of this particular course. So I hope you got all these pointers, right? Okay. So today we will be focusing on unit 1. So that is aromatic hydrocarbons chemistry. So in this session, I will be mainly focusing on orbital structure, resonance structure, and aromatic character. That means which includes Huckel's rule. So these concepts I will be discussing in today's session. Now let's get into the topic. So a large number of compounds have been obtained from the natural sources. They are nothing but resins, balsams, and aromatic oils. So in the earlier days, when these natural products were isolated, scientists were not knowing their exact structure. The active principles which are obtained from the natural sources are having one common property, that is, they are having pleasant smell. Due to this particular pleasant smell, they are known as aromatic compounds. So the term aroma is a Greek word which means fragrant or smell. So even though the scientists, they could not identify the structure, all the active principles which are obtained from the natural products, because they are having pleasant smell, all these compounds are designated as aromatic compounds. And later, when scientists came to know that the structure which is responsible for this particular property is benzene or derivative of benzene. And that is how people started defining the aromatic compounds, as the compounds with structure and properties resembling as that of benzene are called as aromatic compounds. That means any compound which is having benzene ring in its structure, and if it is having properties similar to that of benzene, then that compound is known as aromatic compound. So these aromatic compounds, they produce benzene or derivatives of benzene upon chemical treatment, because the basic unit present in them is the benzenoid ring system. So upon chemical treatment, these aromatic compounds will be converted to either isolated benzene system, or they will yield finally benzene derivative. So these compounds are also known as benzenoids or benzene derivatives. So aromatic compounds, benzenoids or benzene derivatives, all they refer one and the same. Okay. Now, if you look at how benzene was first time it is isolated, benzene was isolated first time by Faraday in 1825. When whale oil is subjected for pyrolysis, benzene is obtained as the product. Now later, Hoffman in 1845, he found benzene from coal tar. Petroleum and coal tar, these are the major reservoirs for the majority of the organic compounds. So whenever these coal tar or petroleum products are subjected for fractional distillations, depending on the temperature at which the material is subjected for fractional distillation, we get different fractions. So each fraction may consist of a single component or mixture of components. So that is how when coal tar is subjected for distillation, from one of its fraction, benzene is obtained. There are also several other products obtained from coal tar. They include polynuclear aromatic hydrocarbons such as anthracene, naphthalene, phenanthrene, and heteroaromatic compounds such as pyridine, pyrrole, furan, and so on. So all these are aromatic or heteroaromatic compounds which are obtained upon fractional distillation of coal tar. Students, now that you learned what are aromatic compounds, now let us get into the core topic, that is orbital structure of benzene. Let me quickly share my screen. Now let's look into the orbital structure of benzene. Benzene structure can be represented like this. That is, we have drawn here a hexagon with 3 double bonds at alternative positions. Okay. Alternatively, benzene structure can also be shown like carbon-hydrogen network. So the second structure. So the molecular formula of benzene is C6H6. Here the central atom in the structure of benzene is carbon. It is made up of 6 carbon atoms. Each carbon of benzene is in sp2 hybridization. Always the doubly bonded carbon atoms will be in sp2 hybridization state. So how this sp2 hybridization occurs? Here one s orbital intermixes with 2 p orbitals, and thus it gives 3 equivalent energy containing sp2 hybrid orbitals. these three sp2 hybrid orbitals will be arranged as if they are pointing towards the corners of a triangle. And that is the reason whenever a particular atom is in sp2 hybridization, the shape will be trigonal planar in shape and the bond angle will be 120 degrees in case of sp2 hybridization. That means with respect to each carbon in benzene, the shape is trigonal shape, but here 6 carbon atoms are arranged in the form of cyclic ring structure. And that is how overall molecular shape, if you see, due to this sp2 hybridization, benzene is a flat molecule with a symmetrical hexagon structure. Now let us see how exactly sp2 hybridization occurs in case of benzene. So for that, let us consider with respect to each carbon how sp2 hybridization occurs. Carbon electronic configuration is given here. Carbon atomic number is 6. So that means 6 electrons will be present. So the electronic configuration is 1s2, 2s2 and 2p2. Okay, so here only valence energy level electrons are shown. Valence energy level means the outermost energy level. It consists of only 2s and 2p electrons. Okay, now if you excite one electron from 2s energy level to 2p, then the electronic configuration it becomes 2s1, 2p3. So at this particular stage, one s orbital intermixes with two p orbitals. So as a result of which there will be formation of 3 equivalent energy containing sp2 hybrid orbitals. Okay, so you can see here one p orbital, that is 2pz orbital, is not participating in the hybridization process. So that 2p electrons, okay, so that 2p electron will be left over as it is along with the 3 newly formed sp2 hybrid orbitals. So the newly formed sp2 hybrid orbitals are shown with orange color orbitals here, while the blue orbital refers to the unhybridized p orbital, which is present along with each and every carbon. When you visualize the orbitals along with the axis of the p orbitals, we can see only 3 newly formed sp2 hybrid orbitals where they are arranged with a bond angle of 120 degrees. But from side view, you can see all types of orbitals here. 3 sp2 hybrid orbitals you can see here, and also the unhybridized p orbital, which consists of 2 lobes above and below the plane. So this is how, with respect to each carbon in benzene, the hybridization is sp2. That means 3 hybrid orbitals will be there, along with that 1 unhybridized p orbital will be present at each carbon. Okay, now let us try to draw all these hybrid orbitals and the unhybridized orbital with respect to each carbon. Now, when you draw all these 3 sp2 hybrid orbitals, this is how we get. Okay? All carbon atoms in benzene are equivalent. Just for convenience purpose, let us number the carbon chain. So 1, 2, 3, 4, 5 and 5th carbon. Okay, so at first carbon, you can see here, this is one sp2 hybrid orbital, this is another sp2 and this is the third sp2 hybrid orbitals. Similarly, with respect to second carbon also, we can see 3 sp2 hybrid orbitals. Okay, so like this, at every carbon, first draw 3 sp2 hybrid orbitals. Now, once you complete drawing all the sp2 hybrid orbitals at all these 6 carbon atoms, you can see while drawing these hybrid orbitals, there will be overlapping of sp2 hybrid orbitals between the neighboring carbon atom. Okay, so this is sp2 hybrid orbital of the second carbon is overlapping with the sp2 hybrid orbital of the third carbon. So this is how due to sp2 overlapping, we get a sigma bond. So that is how all the carbon atoms will be involved in the bond formation due to the overlapping of the sp2 hybrid orbitals of the neighboring carbon. That means at each carbon, 2 sp2 hybrid orbitals out of 3 will be overlapping with the neighboring carbon atoms sp2 hybrid orbitals. Okay, so at each carbon now, one sp2 hybrid orbital is left over. Okay, now what happens to this particular sp2 hybrid orbital? There are 6 hydrogens present in benzene. Okay, and each hydrogen consists of an s orbital. So now the leftover sp2 hybrid orbital at each carbon atom, it overlaps with the s orbital of hydrogen. So like that, all the 6 sp2 hybrid orbitals which are left over at 6 carbons, they overlap with the s orbitals of 6 different hydrogens. So that is how we get 6 CH bonds. Okay, that is how we get CH bonds. Okay, which are sigma bonds in the structure of benzene. Okay, now here we have finished showing the bonding of all the 3 sp2 hybrid orbitals with respect to each carbon. As I mentioned previously, each carbon is having one unhybridized p orbital also. So now these p orbitals which are present present at each carbon are responsible to make pi bonds. Okay, so here in the next diagram, only the p orbitals present at each carbon are shown, while the sp2 hybrid orbitals are not shown, just to avoid the confusion. P orbital consists of two lobes. The above lobe is shown with yellow color and the below lobe is shown with blue color. So what happens here is all the p orbitals of the neighboring carbon atom, they overlap with each other. Okay, so that is how there will be pi cloud above as well as below the plane of the molecule. And that is how we can see delocalization of the electrons throughout the carbon chain in case of benzene. All the sigma bonds in benzene structure are formed due to the overlapping of either sp2 or sp2 hybrid orbitals of the neighboring carbons, or due to overlapping of sp2 hybrid orbital of carbon with the s orbital of hydrogen. Okay, that is how we get carbon-carbon and carbon-hydrogens sigma bonds. Okay, while in case of pi bonds are formed in the structure of benzene due to the sideway overlapping of p orbitals which are present at all the 6 carbon atoms. Okay, so this is how the orbital structure of benzene can be shown. Okay, so orbital structure can be shown by integrating both sp2 hybrid orbitals as well as p orbitals overlapping, or in one diagram you can show only sp2 hybrid orbitals overlapping, while in another diagram you can show only the p orbitals overlapping. Okay, so if you want to show all the orbitals overlapping in one structure, you can refer to the another video which I have already given on my YouTube channel. The link is provided in the description. So where I have shown the entire thing on the board. Okay, so you can better clarify your doubts by going through that particular video. So students, I hope from this you might have learned how to draw orbital structure of benzene. So if you have any doubts, you can keep in chat so that from time to time I'll be answering your doubts, or I'll be answering your doubts at the end of the session. Now let's get into another important topic, that is resonance phenomena in benzene. So this is one of the most important and a definite question in your university examinations. Okay. Some of the organic compounds, they exhibit more than one structure. So that particular phenomena is known as resonance. So it is the phenomena by which molecule can exist in two or more than two Lewis structures. And what is the difference in these structures? If you see, these structures are differ in the arrangement of electrons. That means the molecular formula of the structures will be similar. The structures will differ only in the electrons arrangement. Okay, so that means structures which differ in only arrangement of electrons. So those structures are known as resonance structures. Now that you learned about resonance and the resonance structures, now let us draw resonance structures of benzene. So these are the two resonance structures which are given by Kekulé. So they are also known as Kekulé structures of benzene. So how we can draw the Kekulé structures? First make a hexagon, because the molecular formula of benzene is C6H6. So that means it consists of 6 carbon atoms. By using 6 carbon atoms, you can make hexagon first. And then keep double bonds at alternative positions. Okay. Now other resonance structure how we can draw is just to shift the double bonds to the adjacent position. Because what is the definition for resonance is, here the molecule can have two or more than two structures which differ in the electrons arrangement. Okay, that means here just to shift the pi bonds to the adjacent positions. Wherever single bonds are there, there keep double bonds. And that is how we get a new resonance structure for benzene. Okay, so this is how at the 3 alternative positions we can shift the double bonds, and thus we get the second resonance structure. Okay, so these two are the Kekulé structures of the benzene. Okay, now these two structures can be represented with the help of a resonance hybrid. Okay. So how we can make this resonance hybrid structure is just by combining the structural features of both Kekulé structures. In the first Kekulé structure, double bonds are present at 1, 3 and 5 positions. Now if you look at the second structure, the double bonds are present at 2, 4 and 6. That means what? If you combine both these structures, it is like every carbon atom is a doubly bonded carbon atoms, or through the all 6 carbon atoms double bond is present. That means to represent that we can make a circle inside this particular hexagon. Okay, so that is how we can draw the resonance hybrid structure for benzene. So it is because of this delocalization of electrons or resonance phenomena, benzene molecule is highly stable when compared with the unsaturated compounds. Because unsaturated compounds also consist of double bonds, benzene structure also consists of double bonds. But yet benzene is more stable when compared with unsaturated compounds. It is because of this resonance phenomena. Now, we often come across with a word that is known as resonance energy. So the resonance energy of benzene is 36 kilocalories per mole. And what is the meaning of this resonance energy is the energy difference between the real benzene molecule. Real benzene molecule means here the resonance hybrid structure, that is considered to be the real benzene structure. So the energy difference between the real benzene structure and the hypothetical Kekulé structure. So these two structures energy difference is known as resonance energy. So the resonance energy of benzene is 36 kilocalories per mole or 151 kilojoules per mole. So the resonance energy can be represented by kilocalories per mole or kilojoules per mole. Make a note of resonance energy of benzene because in the next coming modules, you will be using this particular value. Higher the resonance energy, higher will be the stability of the molecule. Okay, so when compared with unsaturated hydrocarbons, benzene is stable because of its resonance phenomena or resonance energy. But if there are several aromatic compounds are present, that is benzene, naphthalene, anthracene, phenanthrene, all these are aromatic compounds only. To finally know which of these compounds is highly stable, we will be using this resonance energy value. Okay, so save it for the later use. Students, here is a quick question for you. So which of the following representation of benzene structure is correct? Okay, give your answers in the chart, whether it is A, B or C. So one of the structure, if you say it is having dot. So this is how some of the students will represent, but it is wrong way of representation. Okay. And the another structure is where the double bonds or the circle is drawn very inside the benzene ring system. That means this double bonds or the ring system is away from the skeleton hexagon structure. What is this hexagon structure meaning? 6 carbon atoms are in benzene. How they are connected to each other, that is represented with this hexagon. Okay. Now the circle or the double bond are that we are showing the delocalization of pi electrons. Okay. So this delocalization of pi electrons will be always very close to the carbon skeleton. That means this circle always you have to draw nearer to the hexagon structure. That is the correct representation of the structure. Okay, that is why this structure is the correct representation of the benzene. Okay, so never ever write the benzene structure with a small circle inside the hexagon structure. That is wrong way of representation of the structure. And most of the students usually represent like this. Okay, because they don't know the importance of that circle, why a circle is kept, okay, and how it should be kept. That you should be aware first. Now, if you have any doubts related to resonance structures also, you can give in the chart window. Now, let's jump into the last topic of today's session, that is aromatic character and Huckel's role. Now that you have learned about resonance structures of benzene, resonance energy of benzene and orbital structure of benzene, the next important property is known as aromatic character. This particular term used to describe cyclic planar molecules which is having delocalized pi bonds. And also these structures exhibit more than one structure. That means they exhibit resonance phenomena. So there are three different types of theories are there which can explain the aromaticity or aromatic character of the compounds. These are aromatic sextet theory, Huckel's rule, and finally valence bond theory. Now let us see briefly what are these three theories which explain aromaticity. Now first let me discuss about aromatic sextet theory. Sir Robert Robinson was the first person who coined the term aromatic sextet in 1925. So this particular theory qualitatively describes the aromatic character of the benzenoid species. So according to this aromatic sextet theory, when a compound is having sextet of electrons, then it is said to be aromatic. Now what is the meaning of sextet? It means a group of 6 electrons which resist disruption. That means compound should consist of a closed group containing 6 electrons. Then it is said to be aromatic in nature. So as per this particular theory, if you look at the structures of benzene, toluene or pyridine, so here Lewis structures are given where the p electrons are represented with the help of dots. So in the first structure benzene, you can see a hexagon is written. The pi bonds are not shown here. Instead, the p electrons are shown because in order to make you clearly understand how the ring is generated with these 6 electrons. Okay, so you can see in the benzene structure, as I mentioned, under orbital structure of benzene, each carbon is in sp2 hybridization state. So there will be 2 out of 3 sp2 hybrid orbitals will be overlapping with the neighboring carbon atoms. So that is how neighboring carbon atoms are bound. bonded with each other. Okay. While the other third sp2 hybrid orbitals overlap with the s orbital of hydrogen. So that is how CH bonds are formed. Okay. So in addition to these three sp2 hybrid orbitals, each carbon will be having one p orbital. Okay. So that p electrons are shown here. Okay, instead of showing the overlapping, here p electrons as such are shown at each carbon. So you can see in the benzene structure, a closed group containing 6 electrons is maintained. So that is how a sextet is maintained, and that is the reason, as per aromatic sextet theory, benzene is considered to be aromatic compound. Same is in case of toluene also. So in case of toluene also, it consists of 6 electrons, 6 p electrons. So the ring is having 6 electrons. Okay. And in case of pyridine also, all 5 carbon atoms are having p electrons, and similarly the nitrogen is also having p electron. Okay. So all these p electrons are contributed towards the delocalization, and that is how the ring consists of 6 electrons. And that is how a sextet is maintained in all these compounds. So wherever the compound maintains, in whatever may be the compound, the sextet is maintained, those compounds are considered as aromatic compounds. Okay, so it is this particular sextet which is responsible for the aromatic properties based on the aromatic sextet theory. Okay, and this kind of sextet, that is a group of 6 electrons, are not maintained in case of aliphatic and alicyclic compounds. It is maintained only in case of aromatic as well as heterocyclic compounds. Even the pyrrole, furan, thiophene, also this sextet is maintained. And that is the reason, even though they are heterocyclic compounds, they are considered as heteroaromatic compounds. So a German scientist, Erich Huckel, is the one who proposed this particular rule, and that is why it is known as Huckel's rule. This particular rule explains the aromatic properties of planar molecules. Now, what is this rule? As per this rule, a molecule is said to be aromatic if it is meeting with 2 criteria. The first one is the molecule should have continuous cyclic cloud of delocalization of pi electrons above and below the plane, and this cyclic cloud must contain a total of 4n plus 2 number of pi electrons. That means either 6, 10, 14, 18, 22 number of electrons can be present in the cyclic cloud. Then the molecule is said to be aromatic in nature. Now let's see a few examples of aromatic compounds and how they are obeying the Huckel's rule. So let's see how benzene is considered to be aromatic as per Huckel's rule. So this is the structure of benzene. So I have written here one of the Kekulé structure of benzene. There are few simple tips are there to make out whether a compound is obeying Huckel's rule or not, so that we can easily make out its aromaticity. So as soon as the structure is given, first you see whether the molecule is cyclic. Okay, and then whether conjugated double bonds are maintained or not. That means the molecule should have conjugated system. And the third one is this particular pi electrons, total number of pi electrons should be equivalent to 4n plus 2. Okay. So when a molecule is meeting with all these criteria, means it is obeying Huckel's rule, and thus it is said to be aromatic in nature. So here one of the Kekulé structure of benzene is written. So you can easily make out from its structure that it is cyclic in nature. And here 3 double bonds are present at alternative position. That means conjugated system is present in the structure of benzene. Now coming to the third important criteria is the total number of electrons, pi electrons, should be equivalent to 4n plus 2. Okay, so here this particular molecule is having 6 pi electrons. How 6 pi electrons are present? Because here the molecule consists of 3 double bonds. Each double bond is equivalent to 2 electrons, and that is how overall it contains 6 pi electrons. Now when you equal 4n plus 2 equals to 6, then we will get n equals to 1. Okay, when you simplify this particular equation, finally we get n equals to 1. That means it is obeying Huckel's rule, and that is how benzene is considered to be aromatic in nature. Now let's see in case of some of the polynuclear aromatic compounds like naphthalene and anthracene. So this is the structure of naphthalene. So you can see naphthalene is also cyclic molecule. Okay. And here at alternative position conjugation is present. That means it is a conjugated system. Okay. Now if you count the total number of double bonds, this particular molecule is having 5 double bonds. 5 double bonds accounts for 10 pi electrons. Okay. Now if you make that 4n plus 2 equivalent to 10, okay, then we get n equals to 2. That means even naphthalene is also obeying the Huckel's rule, and that is how it is considered to be aromatic. Okay. Now coming to the other polynuclear aromatic hydrocarbon, anthracene. This is the structure of anthracene. Anthracene is a tricyclic system. So it is also a cyclic system, and it consists of conjugation because at alternative position double bonds are present. Okay. So it is meeting with the first 2 criteria. Now coming to the third criteria, the total number of double bonds are 7 here. Okay, 7 double bonds are equivalent to 14 electrons. Okay, so that 14 electrons means when you make 4n plus 2 equivalent to 14, then you will get n equals to 3. Okay, so that means even anthracene is also obeying Huckel's rule, and thus it is considered to be aromatic, similar to benzene and naphthalene. Now from this particular table, can you make out what is n here? So in case of benzene, we got n is 1. In naphthalene, we got n equals to 2, and anthracene n equals to 3. So you might have guessed it right. Yes, n is the number of rings here. Okay. So in case of monocyclic rings such as benzene, we get n equals to 1. Okay. Bicyclic fused rings such as naphthalene consists of 2 rings. Okay. And in case of anthracene, because it is a tricyclic system, there we got n equals to 3. Okay, so this is in case of neutral species. The third theory is known as valence bond theory, where scientists came to know the exact bond character and bond lengths in case of benzene. So based on the X-ray crystallographic studies on the structure of benzene, we came to know that benzene consists of a regular hexagon where carbon-carbon hydrogen bond angles are 120 degrees. And all hydrogens are lying on the same plane. That means benzene is planar flat molecule. Of benzene is established based on X-ray crystallographic study. And through this particular study, we came to know that all carbon-carbon bonds, that means there are 6 carbon-carbon bonds are present in the structure of benzene and 6 carbon-hydrogen bonds are present. All 6 carbon-carbon bonds are equivalent and also all carbon-hydrogen bonds are equivalent. This is what we came to know based on the X-ray crystallographic studies. Now coming to the bond lengths in case of benzene, it was found through these particular studies that all carbon-carbon bond lengths in benzene are equivalent to 1.397 angstroms. Now, if you look at the structure, these are the Kekulé structures of benzene and the resonance hybrid of benzene. Originally, if you look at the bond lengths in case of single bond, it will be 1.54 angstroms, and whereas for double bonds, it will be 1.33 angstroms in case of alkanes and alkenes. Okay. As per the Kekulé structures of benzene, this particular benzene is supposed to have 3 single bonds and 3 positions double bonds. There is no single carbon-carbon single bond accounted in the structure of benzene as per X-ray crystallographic study. That means all carbon-carbon bonds in benzene are having double bond character, which can be exactly reflected through its resonance hybrid. So in case of resonance hybrid, we will write a hexagon with a circle inside it. A circle which is covering all the carbon atoms. It means that all the carbon atoms are having double bond character. Whereas in the Kekulé structure, we keep double bonds at one particular position. That means these bonds are not delocalized bonds, but they are localized bonds in case of Kekulé structure. And we kept them at 3 alternative positions. Okay, that means the original true structure of the benzene, which we came to know through extrographic studies, is the resonance hybrid structure of the benzene. It is not the Kekulé structure of the benzene. We get the resonance hybrid structure by combining both the Kekulé structures of the benzene. So dear students, we will stop here for today. Please share your feedback and also your questions, if any, in the chat. So meanwhile, I'll be discussing how to answer these topics if you get in the examinations. So when it comes to orbital structure of benzene, the main thing that you have to mention is that carbons which are present in benzene are in sp2 hybridization. Then start explaining about sp2 hybridization. So what is the meaning of sp2 hybridization and how that sp2 hybridization occurs. Okay. Now you can give step by step the way how I explained in the previous session. You can at least remember the orbital structure. Okay, after drawing the complete orbital structure, you will get a picture. No, so at least you should be able to reproduce that picture. Okay, so you can represent the whole orbital picture, including all the sp2 hybrid orbitals, unhybridized p orbitals, overlapping of all these orbitals in the same diagram. Okay, so for that you can refer YouTube video where I have given clearly in the YouTube video, or in the previous session I explained. So you can show all the single bonds separately, overlapping or formation of the single bond separately, and the multiple bonds, that is overlapping of the p orbital separately, just to give more clarity. Orbital structure means it includes both, in fact. Okay, just for your clarity I have shown them separately, but you can put them together and show as a single orbital structure picture also, and this is one of the most important question. So all these 3 topics, okay, orbital structure, resonance structures, and aromatic character in Huckel's rule, you will be getting either for 2 marks or 5 marks. Okay, now when it comes to resonance structures of benzene, what is the definition for resonance? First, you have to write that resonance definition and resonance structures definition, and then give resonance structures of benzene along with the resonance hybrid structure. Okay, dear students, never ever miss resonance hybrid structure. Whenever you are giving the both K-class structures, give resonance hybrid structure also. That is very, very important. Okay, so these are the core things that you have to present under resonance phenomena. Okay, now if possible, mention what is the resonance energy of benzene depending on the marks, and also what is the meaning of resonance energy. Okay, the definition is there, no? So that also you can mention depending on the marks. Now, when it comes to the aromatic character, so this aromatic character can be explained with the help of three theories, but out of these three, the most important one examination point of view is Huckel's rule. Okay, so what is the definition for Huckel's rule? Okay, what is the importance of Huckel's rule? That means the compound whichever is obeying Huckel's rule is considered to be aromatic. Okay, that is the importance of Huckel's rule. Now, what is Huckel's rule? That you have to mention. Okay, so that means any compound, if it is cyclic, conjugated, and having 4n plus 2 number of pi electrons in its cyclic log, then it is following the Huckel's rule. So that you have to state it clearly. So state the rule clearly, and then what is its relation with aromaticity. Okay, so that is the definition of Huckel's rule or aromaticity. Then followed by that, give few examples the way how I have given. So I have given benzene, naphthalene, and anthracene in this particular live session, but you can also give some other compounds also, like pyridine you can take as an example, aniline also you can take, or pyrrole also you can take, any charged species also you can take as an example, and you can explain their aromaticity as an example under Huckel's rule. Okay, so examination point of view, Huckel's rule is very, very, very important one. So students, once again, so students, you can keep your doubts in the chat window. And soon after this class, please spare 20 more minutes before you attend tomorrow's class, just for revising whatever happened in today's session. Okay. So the students who are already written sessional 1 examination and scored well, they might be well aware of this topic. So it will be more or less like a revision for them. So the students who have not attended first internal examinations in your colleges or not performed well in your first sessional examinations, take these classes seriously so that you can get maximum benefit out of these classes. So if this session is added value to you, please subscribe my channel and share to your friends also. Whoever is struggling with POC, please help them also. Okay, so ask them to subscribe my channel so that they can also attend from tomorrow onwards all the live sessions. Keep sharing your feedback. So dear students, keep sharing your feedback and also post your questions, if any, in the chat so that I will be answering them. Okay. So if I miss any of the questions in today's session also, don't worry, I'll be answering them in the tomorrow's session. Before beginning of the session itself, I'll try to answer. Okay, so you can find always from time to time in the chart. One important reminder, student. So quiz will be enabled soon. So before you attempt a quiz, try to revise the concept. Whatever you learned today, try to revise the concept. Then based on those learnings, try to answer the quiz. So thank you so much for attending this live session. Thank you for your sincerity. So study with clarity, not with fear. Okay. Okay, you can check the chart for answers. And you can also, others also keep posting your doubts if any. And please share your valuable feedback. So if today's session is useful to you, then subscribe my channel and also please share to your friends. Those who have not attended today, at least they can subscribe my channel and they can attend for these live classes from tomorrow onwards along with you, so that you will get more study partners also. And in tomorrow's class, And in tomorrow's class, I'll be explaining about benzene reactions. Okay, that is benzene, why it will undergo electrophilic substitution reactions, what is the mechanism involved in electrophilic substitution reactions, and what are the examples under this category of reactions. Okay, so these things I'll be covering in tomorrow's live session. Okay, don't miss tomorrow live sessions. Again, examination point of view, it is a definite question in your final examination. Okay, take care. I'll meet you in my next live session.